Okay, 17C people, here's a linearization of a vector value function. I started recording this before and then thought I was making a mistake, so I stopped it. I'd already written some of it out, but I didn't want to start again or rewrite it because it looks, I think, pretty good. So here's the idea. You've got some function, some vector value function, meaning the function of x and y has two different results. You have this first function here, which often people call f1 or h1, h2, I don't know. I think your professor's using h, I like f. So like this is f1, this is f2, and then I typically write it with this vector notation. So again, we've got the vector f1 and f2, where f1 and f2 are functions of x and y. And then the linearization is, again, the vector value function f evaluated at the point x naught, y naught. My x naught, y naught is going to be 0, 0 here. So I should say the linearization of the vector value function at x naught, y naught equal to 0, 0. So this here, right, this is going to be really the vector f1 at 0, 0, f2 at 0, 0, plus the Jacobian, which is the matrix of the partials. You can also think of it as the gradients as rows. Sorry, so the first row of this 2 by 2 matrix is going to be the gradient of the first function. So it's going to be the gradient of f1 evaluated at 0, 0. And then the second row is going to be the gradient of f2 evaluated at 0, 0. Times the matrix x minus x naught, y minus y naught. And it is matrix multiplication, it's not a dot product. When we write it as a dot product, it's because there's only one vector here, and it's this vector dotted with that vector. But here, since it's matrix multiplication, it's a slightly different, but still essentially the same thing. So in this particular example, the linearization of xy, well, let's see. F at 0, 0 is cosine of 0 minus 0, so cosine of 0 is 1. And f2 of 0, 0 also happens to be, I was going to make this a minus sign. Let's make that a minus sign just to make it a little more interesting. Sure. So f2 of 0, 0, it still doesn't change anything, sorry, is e to the 0, which is 1, minus 0, which is still 1. I was trying to make those different. Oh well, they came out to be the same. And then, that's a minus, it's a minus. The Jacobian, again, it's a 2 by 2 matrix of partials. So it's the partial of the first function with respect to x. So that's going to be negative sine of x squared minus y times the derivative of x squared minus y, which is 2x minus 0. And then the next entry is the derivative of that with respect to y. So it's going to be minus sine of x squared minus y times the derivative of x squared minus y with respect to y, which is negative 1. And then the next row, the partials of this, so the derivative of e to the xy is e to the xy times the derivative of xy with respect to x is just y, minus the derivative of y, which is 0. And then this last entry here is, again, the derivative of e to the xy is e to the xy times the derivative of the stuff, but now we're doing with respect to y, so the derivative of this is just x minus the derivative of y is 1. And then we're going to evaluate that all at 0, 0, which is going to end up being not very interesting because I picked poorly. Oh well, that happens sometimes. So here's what we get for the linearization. It's 1, 1 plus, let's see, if I plug in 0, sine of 0 is 0 times 0 is 0. Sine of 0 is 0 times negative 1 is 0. E to the 0 is 1 times 0 is 0. And e to the 0 is 1 times 0 is 0. Minus 1 is minus 1. Oh good, our matrix isn't all zeros. So then our answer is, I mean, I would maybe leave it like this, but you can write it out. So it's 1, 1 plus, so when I multiply this matrix by this matrix or vector, I get 0x plus 0y in the first entry, and 0x times plus negative 1 times y. So my answer, if I want to write it as one result, is 1 plus 0x plus 0y, which I would normally just write 1, but I want to kind of show the whole thing. And this would be 1 plus 0x minus y. So not very interesting. The linearization of the first part of the vector value function is just 1. The linearization of the second part of the vector value function is 1 minus y. So that's how you do a problem like this. I hope that helps clarify things a little bit.